Markov-Chain and the hard disk universe. Yeah. So let me introduce, because probably the people here, they don't know the background of Werner, who are going to talk about. No. Who is a physicist interested in hard disks. So we met in a conference also related to point configuration. And like one of the things that he's most famous about is for finding faster methods for making Markov-Chain Monte Carlo converge faster and thermalize. And so find basically the ground state or like the equilibrium state better of, for example, ensembles of hard disks that are moving around. Is this correct? Yeah. So this is something that is very famous in the community, but not in the mathematics community, right? Anyway, so here we are.
Well, thank you very much, Professor Krauth and Monte, for having me come here. And so I still have the memory when we first met, right? We first met on Zoom, and then we had real meetings in Paris. Now we meet. So I have an almost impossible mission to do. First of all, to keep you awake at the end of the afternoon, and second, to speak from another community. Even though I think there is no community, there's just results, and there shouldn't be that much of a community. So what I want to explain is, let's say, it's very related to what you are discussing. It's the next generation. Once you have your optimum point configurations, what we call the temperature equals to 0 solutions, what will you do at the next step? What you'll do is you add a little temperature, you make the box in which you evolve a little larger, and then you see what the solution comes out. So this will naturally involve much more than what you have, but it will again involve the question of statistics, of measures, of probability distributions, and from a practical point of view, it will involve the questions of Markov-Chain Monte Carlo. So I wanted to prepare some kind of union of these two problems, Markov-Chain Monte Carlo and the hard disk universe. And so what one of the first reference I have put down here is some kind of historic perspective where we go over 70 years of Markov-Chain Monte Carlo on the hard disk model, and that's what I want to share with you. How do I move a moment?
I guess the arrows.
Arrow. I push all the arrows.
Yeah, it happened again.
Okay, so I do it yes. Again. You can do it. I can. All right. So this is. I'll show you a number of first pages of papers. So this is the first page of the very famous Metropolis et al. Paper from 1953. Which has given rise to the Metropolis algorithm that some of you know. It's the first paper on Markov-Chain Monte Carlo. And it gives the general methods suitable for fast computing machines to compute the equations of state. And it presents results for the two-dimensional rigid sphere. So what did these people do? So as I said, this is one of the most famous papers in all of physics. Excuse me. All right, so I have to go this. So they did, as I said before, they took the box. They looked at not at the packing of hard disks. They looked at the behavior of hard disks in a certain box of given volume, and they wanted to measure what was the arrangement of disks in this box. And they invented the concept of sampling, and this concept of sampling started from an initial configuration. And from this initial configuration, they took one disk, moved it a little bit to the right, to the left, up and down, and introduced one major innovation. So when the move that they proposed was incompatible with the box, or it was incompatible with where the particle wanted to move, then the next configuration was simply the old one. So that is the birth of the Markov-Chain Monte Carlo method, 1953. And then, as we were in physics, you always have to present a new innovation, a new calculation, and an application. And the application was this equation of state that is written 3 times in this abstract already and in the title. So what is the equation of state? The equation of state is the pressure as a function of the volume. Now I realize that maybe you don't know what the pressure is. Well, the pressure is simply, you take your box with your discs inside, you take out a rift, you cut out epsilon, a little slice of epsilon, you push your box together, and then you compute the probability with which this configuration that you end up with is no longer a hard disk configuration. So in this case, for example, it's no longer a hard disk configuration because these 2 disks overlap. Well, you simply take the measure of all the hard disk configuration, you shrink your box, you divide by the rift volume, and then you have the pressure. All right, so that's what an equation of state is, simply computing the pressure as a function of the volume. And the connection with what we've heard all over the day, and probably what we'll hear later during the whole week, is what is infinite pressure? Infinite pressure is the packing problem or the energy minimization problem that we have been discussing. So what this, ladies and gentlemen, did 70 years ago is they wanted to generate samples of hard disk configurations, then take out the rift and measure how many of them went away. Then they wanted to compute phase function, so we will go forward. So now, as I said, I wanted to talk about Markov-chains. So let's discuss. So there's Markov-chain are defined with sample spaces. I call them omega. We can think of it as just as the positions of the disks in the box. Then the Markov-chain is considered as just simply how you do the moves, or in more correct words, it is you start from, it's a sequence of random variables. You start off with a random variable x0, which is distributed with some distribution pi 0. Then you move to an x1, which is distributed with a pi 1, x2, which is probability pi 2, and so on and so on. Xt plus 1 depends on xt through a transition matrix. And then you hope that in the limit of t going to infinity, you have what we call the Boltzmann distribution, or what you probably call the uniform distribution under the condition that no 2 disks come closer than 2 times the radius. So then I will discuss a little bit just so we have this transition matrix. This transition matrix helps you to get from one probability distribution at time t to the probability distribution time t plus 1. But this transition matrix is set up of 2 terms. First of all, it's a probability with which you propose a move. So this proposed move, I don't dare to go back. So the proposed move is you make this epsilon move. You have a disk here, and you propose this move by epsilon going up. So that is what I would describe by this script A. And then you have a filter. This is what we call a filter. And the filter is whether you accept the move or you reject the move. So in our simple case, the filter works like this, that if you have an illegal configuration, then we simply reject the move. So this is called the Metropolis filter, but there are also heat path filters, there are other filters, and we will discuss that in a little bit. And then the Monte Carlo rejections is simply that well, you propose a move, and then if this proposed move is not rejected, is not accepted, then you simply don't do anything. You stay where you are. And so some time ago, I wrote a book, and I was going ahead of myself, and I thought that these rejections were the key element of Markov-Chain Monte Carlo. And sure enough, 1 year later, I started off what I discussed a little bit. And all the modern Markov-Chain Monte Carlo algorithms have no rejection at all. They've completely gone over it. So now let's discuss this double rule of the transition matrix. And I hope I don't tell you things that you're completely uninterested in. But it's such an interesting story. So there has a double role. The first role is that it's the transition matrix that moves the probability distribution pi t into the probability pi t plus 1. And the key, of course, with again the two things. First of all, in the limit of t going to infinity, you get the uniform distribution, what we call the Boltzmann distribution. Each configuration should be the same. But of course, all these probability distributions are completely unknown to you, to me, to everybody, except of the probability distribution at t equals to 0, because that's your initial configuration. Most of the time it's a delta function. That's one aspect. Second aspect is that this probability, this transition matrix is the explicit probability to move from I to j. So if Pij is 1/2, then you have a 1/2 probability if you are at I to move to j. So that's really. So now let's do, which I told me I should give a little introduction to Markov-Chain Monte Carlo, so I do it my own style. So irreducibility. Irreducibility means the transition matrix is irreducible, that if any I can be reached from J or any J can be reached from I, that's irreducible. And then if you are irreducible, then you have a unique stationary distribution which satisfies that pi I is equals to the sum of pi j p j I. We'll go into more detail onto that. So first question is, this algorithm that I talked to you about, where you take one disk and you move it by epsilon, is this an irreducible algorithm? Well, you look into the literature, you come across a real famous paper by Töröczky, which is another Hungarian mathematician, and he gives you these configurations. So this is the configuration of disks at very low density. You can make this into so this is with periodic boundary conditions. Each of these, so this looks convex here, it's convex here, it's convex here, convex here, and each of these disks is held in place by at least 3 other, or exactly by 3 other disks. So this is one of the packing problems, not at highest density. So that was the question, right? So we discussed what is the highest packing, what is the densest packing. And he asked, 1964, he asked the question, what is the lowest packing? Taught himself believed that there was a limit so that you couldn't pack them at lower density. And this is the example where you can see that you can pack disks at essentially 0 density if you have enough space. And this shows also that the metropolis algorithm is not so terribly irreducible.
This is rigid. It's rigid.
This is locally rigid. So you cannot take, because the metropolis algorithm takes one disk and moves it by epsilon. So you cannot take any of these disks and move them. It has a density square root of n, because this goes like this, and this goes like that.
The angle is not.
No. You see it. I mean, just look at it carefully. It goes like that.
Okay.
All right. So we have we just recently we consider this for our algorithm stuff, and we have our programs on it. So it's beautiful paper. But you see, of course, that you take these 4 disks and you rotate them, and you unlock. So this is a locally stable, but not a globally stable configuration. I like your T-shirt, hard disks.
Oh yeah.
I need the same one.
isn't this kind of not in the spirit of the problem, right? If you want to calculate the pressure, you take a slice out of that box. But if you take slices out of this box, like some slices are going to have like a massive mass.
Oh yeah, you're my man. You're my man. So what this shows is that this must be of measure. These configurations must be of measure 0, because of course to get the pressure you have to do an average over all configurations. So this is an infinite pressure configuration, and in order for that the whole ensemble to have a finite pressure, they must be of 0. They must be of 0. Yes, measure. But you excuse me if if I use mathematical terms which are not completely correct. You understand that I'm just a physicist. As I always said, I'm elders 2 as everybody, but I'm just educated. So anyway, so this is so it's not so terribly irreducible. So let's get into another theorem. That's it's my favorite here. It's the ergodic theorem, which kind of is always considered like being a little bit of crap. But so it's if your transition matrix is irreducible, and let's suppose we overcome these problems with this Brodsky configurations, then pi is unique, which doesn't mean that you actually converge to pi, but there's the ergodic theorem, which means basically it means that you have a strong law of large numbers, and any time average of a given single simulation that runs will approach its expectation. So here I have what it means. So I have some time series of which I know the expectation. So I computed the time series. So here, as you get this result, you write the first paper. Then something happens, and you write a second paper, and then you write this. And so I'm not joking. I'm completely serious. But I'm completely serious. But what it means is that in the limit of infinite number of papers, if you don't start again a new calculation, but if you use the old calculation, in the limit of infinite number of papers, the paper that somebody will write is actually correct. Okay. So but it's really interesting that it's the strong law of large numbers. So it means a single simulation, a single time series will, after a certain time, will go closer and closer to the expectation. I continue later. So now talking about first paper, second paper. So this is the conclusion of the Metropolis et al. 1953 paper. And it says there is no indication of a phase transition. Well, they did this calculation and they found out that the pressure did not have any funny stuff happening. So there's no indication of phase transition. So that's the first paper. So recently, we were interested in looking what actually came out of this. So this is the Metropolis et al. Result. So this is the volume. And then this is the pressure, and then you look at whether something funny happens. And so they didn't see anything funny happen. But what actually happens is, so redone just this here, is this curve, and this coming up and down maybe looks like a phase transition. But we can learn something really interesting from this. So this may be related to what some of you do for your living. So what's really interesting is that if you have a configuration here of hard disks or whatever hard disks in the box. So this is in the square box of 224 particles. That's just like the Metropolis et al. Paper. Then you know that you have two different types of configurations. We call them the base configuration and the tip configuration, right? So the base configuration is you draw little hexagons of the local environment, and then they can sit on their base. And here I showed they all sit on their base, almost all of them. And here they sit on their tip, right? And now, of course, what you can, if you are in a square box, you can simply take this configuration, you can rotate it in the square box. And that's what allows you to understand that you should have as many configurations that are base as you should have configurations that are tip. And you transform this, you know, as I said, I'm weakly educated, but I have a working knowledge of complex numbers. So, so then you work this into what is called the local orientational order parameter. And you understand that this one has a psi 6 of 1, and this one has a psi 6 of -1. So you know that miraculously, if you work in the square box, you know that you have one, you know nothing, you don't know the pressure, you don't know anything, but you know that the expectation of psi 6 must be 0. And for about 10 years, so you should have explained this. So for about 10 years, we have got extreme mileage out of this idea. We said, well, we have the ergodic theorem telling us that we should, if we have reached the mixing time of our Markov chain, then we should reach the expectation value for any number. Right? We are interested in the pressure, but let's just be interested in this quantity and check when we get close to 0. If you're not at 0, then throw away your data because you are just in the first paper, second paper, third paper sequence. You're not yet where you want to be. Anyway, so that's what you can learn from the good papers. So now, but please ask questions. So now, if you followed what I was explaining, there was this 1953 paper by Metropolis saying, well, inventing Metropolis Markov-Chain Monte Carlo algorithm, and also saying there was no phase transition, as it was known that there shouldn't be one. And then in 1962, this means 60 years ago, there was a paper by Alder and Wainwright on the phase transition in elastic disk, where they said, well, you know, everybody says there is no phase transition, but we have seen it. And please take a notice. So this is considered the most, I don't want to give, you know, everything superlative, but, you know, just let me, then I stop. So, but this is considered the most important numerical work ever done, because it was the gods of physics called Landau, Peierls, said there should not be a phase transition. And then they ran their computer and then they found that they did this and it predicted there was a phase transition. And actually, what turns out there is not just a phase transition, there are two phase transitions. But anyway, so that's considered top-notch, Top Gun, as we say, it's Top Gun. And they said there is a phase transition. And so let me show it to you. So this is for 72 particles volume as a function of pressure. And that's the original 1962 calculations here. Check. These are the 1962 calculations. And we just recently, for the 60th anniversary of this paper, we just redid the calculation. It's just beautiful how, if you do a good calculation, people can come up a century later, 2 centuries later, and they will find back what you found, which is a very rare property. But anyway, so this created a lot of excitement over about 50, 60, 70, 80 years, or 60 years. I'll tell you some of it, but let me show you. So this is, so they did calculations on 72 disks, 72 disks. It's not a lot, right? It's just a few disks. And you would think that you can go home, you know, give this to somebody and you'll get the exact solution. Or you take 870 disks. That's what they did also in 1962. And the main point I want to show you is that how difficult already these completely ridiculous problems, I mean, completely ridiculously small problems are. So I tell you, so for example, here it's not very, very big density. We take also 870 disks. And then we have this, we have our, you know, then we actually put our mind to it and we check with this orientational order and all other criteria, you know, when are you going to get from tip to base to tip to base? So we spend, you know, we cannot prove anything mathematically, but at least we can be a little careful. And if you're a little careful with the best currently known Markov-Chain Monte Carlo algorithm, you need a few hours until in this very small system, you can believe that you have seen all of sample space. So just to tell you how difficult this problem is and how difficult Markov-Chain Monte Carlo calculations are in general. So now let's go back to a little bit of discussion on the theory of Markov chains, and I'll talk about probability flows. So I said that if you are irreducible, then you have a condition which is pi I is equal to the sum of pi j pj I. And here in this nota bene, you see where it comes from. Well, if at time t, your samples j out of sample space omega are distributed according to a distribution pi j of t that we don't know, then each point is distributed with pi j of t, and it gets from j to I. That is this. It's not too small for you. That's the connection, and that means that the distribution at time t plus 1 must be pi times so it's the row vector of pi multiplied with the transition matrix. It gives the new row vector. And then if you have a steady state, then you cut off this t, and then you say t plus 1 is equal to t is equal to the steady state limit, which is the Boltzmann distribution that you want. And then you have this distribution. So the condition that we call the global balance condition is that so that you can read it here. It's really strange. It means that the flow into each configuration, into each sample, the flow into each sample must be equal to the stationary distribution, and is, in other words, the Boltzmann distribution. And we have a second formulation, which means that if you use that all transition matrices are stochastic, which means the row sum of the transition matrix is equal to 1, then you can show that the flow that gets out of any sample I must be equal to the flow that goes into any sample. So that's the global balance condition. It's an incompressibility of the flow as you go into a sample I. So what comes in as probability flow must be going out as a probability flow. Besides this global balance condition, what is much more famous is the detailed balance condition. So this detailed balance condition that maybe one or the other of you have heard about. Detailed balance, ever heard about this? Detailed balance condition. That's what everybody studies because it's easier. So the detailed balance condition says that the flow between sample I and j must be equal to the flow from j to I. So the flow from I to j must be equal to the flow from j to I. All right, so this detailed balance implies the global balance condition, and it's 99.999 of algorithm, almost or 99% of algorithms satisfy the detailed balance condition because it's so easy to come up with algorithms. So let me just, so I have one slide on this, the spectrum, and one of the mathematical reasons why the reversible, the detailed balance is the same as reversible transition matrix. So one of the reasons why the reversible transition matrix or the detailed balance conditions are studied so much is because the transition matrix in that case has a real eigen spectrum, and you have a pi, or what's called a pi orthogonality. That means you can expand on the eigenvectors, and you can lead a very happy life studying only reversible transition matrices. So now So this is a little bit of wake up. So the Metropolis algorithm is a famous example of a reversible algorithm. Okay, so this is point number one. The Metropolis algorithm is reversible. And the reason for this is that you move from here to here with the same probability that you would move from here up to here. So you are reversible. But I am sorry to tell you that the algorithm used by Metropolis et al. Is non-reversible. That's quite interesting that they were able to introduce in 1953 this Markov-Chain Monte Carlo. They were able to introduce the concept of reversible Markov-Chain, and in the same paper they were able to overcome the constraints of the reversibility and produce a non-reversible. And to prove it, I show it here because they say we move each of the particles in succession. So what is a reversible Markov-Chain algorithm for this example? So reversible Markov-Chain algorithm is you have 4 disks. At each time step, you take a random disk between 1 and 4. And you move this random disk by a random epsilon. And that is something I can prove to you is a reversible algorithm. Because then the probability to take the same disk is again 1/4, and the probability to move back, and then you have a reversible algorithm. What these clever ladies and gentlemen did in 1953 is they took disk number 1, moved it a little bit. Then they took disk number 2, moved it a little bit. This number 3 moved it a little bit until 224, if you listen to what I just explained. And after 224, they came back to that is a non-reversible algorithm because the reverse of this, first moving 224, then 223, then 222 is completely excluded. So that's what explains that the original algorithm is reversible, but that the algorithm that is used was non-reversible. If you have any questions, please interrupt me.
But is it non-reversible in an important way or in a...
Well, now, of course, in this way, it's not so important, but I'll explain to you in 3 minutes, how it can become. So what I just want to say, this is a non-reversible algorithm. So this is a non-reversible algorithm. I also want to say that moving disks contains 2 random elements. One random element, which is which disk are you going to move next? And second random element is by how much are you going to move it? But thanks for the question, because now this is blocked here. I have to stop my talk. It doesn't want to move. No. It doesn't move. Right. Okay.
Now the arrows move suddenly.
But now
it's a non-reversible process.
But now it moves in the wrong direction.
But try to do the arrows. The arrows was moving when I said.
Okay. So let me, in my little pass through Markov-Chain Monte Carlo, let me discuss total variation distance. Total variation distance, that maybe you are much more familiar than I am, means that you look at, so as I told you, you start with pi0, then you go to pi1, pi2, and you want to know how close are you to the stationary distribution. Well, what you simply do is you take your whole configuration, sample space, take absolute values and sum over the difference with a 1/2, and that gives you the total variation distance. I learned that from Percy Diaconis. And then you say, well, once the total variation distance is less than 1/2, let's say it's 1/4, starting, that's the point that I want to get at, starting from the worst initial configuration. So you do something that you don't want to do is you don't want you know, you want to solve the hard disk sample problem, but you start with some really horrible initial configuration, and then you check until when am I getting close to my initial configuration, and then this is called the mixing time. Unfortunately, there are now since about 15 years there are colleagues of you who write books on Markov-Chain and tell you it's the mixing time that's really important to converge. So there's no point in what I'm trying to explain with this transparency is there's no point in starting off your Markov chain from some kind of well-designed initial configuration. You can just start it off with the pits, with the worst initial configuration, and you will not do much worse than if you chose the best one. That's a point I cannot make in physics conferences. That's why I will talk to you. And it's really true. It's really true. So now let's do this. And let's move from 870 to just 1 million particles. That was mentioned, that was a number that was already mentioned before. So here we have 1 million disks. And then I use what I consider the worst initial configuration and the worst initial configurations from another point of view. So some really horrible configuration. And I wait until they get close to each other in some number. And good enough, they actually come close. So this is some quantity, and this quantity should be, become the same. And fortunately, after a certain number of sweeps, it becomes the same. And then you look at how many sweeps this are, and I did the algebra for you. So a Metropolis algorithm on a single CPU on my laptop does about 10 to the 10 moves, 10 to the 10 little funny moves. It means 10,000 per particle. That's a lot. One sweep, what I show here, is 10 to the 6 moves, and 10 to the 9 sweeps takes 11.4 years. So we have an algorithm that is really perfect. That's the Metropolis algorithm. And after about 11 years, we'll start, that's why I'm getting a little older, but after about 11.4 years, you start getting the first configuration. Yes.
And is the worst configuration just putting?
Well, let's say if you are a little bit, if you did undergraduate physics, then we start from a liquid and we start from a crystal. We start off with a crystal, but not the Brodsky crystal. We just start from a little crystal. Here we are at density 0.7, which is just 20% below closed packing. There's a lot of space for everybody. But it's, we start with a crystal, we start with a liquid, and then we wait 11.4 years until we converge. And the point I was making about this mixing time is that I think one shouldn't start outsmarting your calculation until this time has been reached. There's no point, because otherwise you are still stuck in your initial configuration. All right, so we are up the creek here. Excuse me, we are up in a difficult situation. I can tell you later how we compute this 11.4 years, but we didn't run our computers. I made Econ my superior in Paris. Electricity, electricity wouldn't allow you to run for 11 years. But now let's discuss something called, what I've also find quite interesting, it's the conductance. So any just, how much do you still, I started a quarter afterward. I still have a little time. Right? Yeah, you have 2 minutes. Okay, all right. Okay. So now let's discuss conductance. And the conductance thing is any Markov chain. So this is omega. Any Markov chain looks like that. Anyone looks like this. So you have a bottleneck. You have a left side S, which pi of S less than 1/2, and it goes over. So then the flow that gets you from S into non-S divided by pi of S is called the conductance. And it's a really beautiful result by Sinclair and Jerome, generalized by Janet al. 1999. All of this is in the mathematics literature, telling you that your Markov chain, whether it's reversible or non-reversible, has no choice but to mix in a time which is either 1 over tau, 1 over pi, or 1 over phi squared. So it's clear there's only one bottleneck, not many, and they are lower and upper bounds given by this conductance.
Sorry, what was A?
Well, it was just, I tried to be short, but so there's, we can discuss that later. So this is called the set time. It cannot be the mixing time because there are some Markov chains that don't mix. So it's the set time, it's the time to reach the set given multiplied by pi of 2. So it's some generalization of the mixing time.
Okay, so I can sort of think that.
Yeah, you can say kind of thing. But it's really amazing that what, in, let's say, the physics idea is that you have two types of motion. One motion is ballistic. You go from A to B in the time of the length of A to B. The other motion is diffusive. And what these people, ladies and gentlemen, told us is there is any Markov chain is either, is always within the range of ballistic to diffusive. There's no other choice. Beautiful. So now let me get to lifting. I try to be a little fast. So what the lifting idea is the following. You have a sample of sample space. And what you can do is you can cut this sample space into more pieces. So let me go really fast here. You can associate another problem to it that doesn't change the conductance, that doesn't change, and that preserves almost all properties. Let me just go into detail, into explanation. So here is the simplest Markov chain, a single point moving on n vertices of a path path. That's my omega. And the view that we have had until 15 years ago of Markov chain is you have a sample space, patch, omega. And then you have a space of moves that I call L. And it means you move either to the left or you move to the right. So Markov chain Monte Carlo was the following. You had a sample space. Your configuration at time t was here. Then to know what did you do, how you do, you went to your move space, L, you got your move, and then you move either to the left or to the right. That's the way we were brought up. Everybody is involved. What this, so we can discuss that in detail.
So this is like a tuning machine.
No, it's just that's Markov chain. You have moves. Yeah, of course, that's like a tuning machine. But you have a sample space. And that's one part, and then you have moves, and that's another part, and then you get them together through the transition matrix. So Janet al. and the Diaconis et al. 20 years ago, they said, well, let's move. So you see here, here's a red dividing line. Let's get us all together. And this lifting idea is the following, saying, well, okay, so all right, so I skip all of this. I skip all of this. Let's get this together. Let's make a bigger space out of the sample space that I have here, cross the move space. Let's get the move into our sample space, and that's called a lifted sample space. So the lifted sample space is no longer 1 to n, so the positions, but it's times moving up and moving down, moving plus and moving minus. Right? So that's called the lifted Markov chain. It's a non-reversible lifted Markov chain. And then so each configuration or each sample that was up here gets lifted into one where you move to the left and another one where you move to the right. proposed by Diaconis in 2000. So now, so if you are here, then you move to the left, but you conserve your metropolis algorithm, and you remember that in the metropolis algorithm, you move, for example, you move to the left, but sometimes your move was rejected. I told you before, if the move was rejected, then you stayed where you are. But now a miracle appears. So the miracle is that if you want to move to the left, but you cannot because the metropolis algorithm tells you to reject the move, instead of rejecting the move, you change your lifting variable and you move from below up, or you move from up below. That's a complete miracle. And that it actually works can be shown here, but as it is already 5 o'clock, and so that here it shows you that that it satisfies the global balance condition, and that this trick of rebranding every failure, every rejection that you have, you rebrand it into a move from the lifting variable. And this is this new generation of Markov-Chain Monte Carlo algorithm that have no rejection. So here I did it for for single particle in 1D. I can do it also for hard disks, and if you leave me enough time, I can explain that to you. So here is disks, spheres on a 1D, spheres in 1D. That's my sample space: 1, 2, 3, 4, 5, 6, 7 disks.
You can take 10 more minutes.
Huh?
You have 10 more minutes or so.
Okay, thank you. Thank you. I'll take 20.
Okay.
I have a second edition also. But I think so. Now I just want to explain to you that so this move space here is quite rich now, right? The move that you want to do is you move either to the right or you move to the left. And you have the choice of moving particle 1, 2, 3, 4, 5, 6, 7, 8, or 9, or n. And as I said, that Markov-Chain Monte Carlo has been done for 50 years in a way that you take your configuration, then you have a clever algorithm, and then you move. So at each time step you take the configuration, the sample at which you are. You get a new move, and so now there are many choices for non-reversible liftings. That's what I want to explain. So for example, the sequential lifting is omega hat, which means the lifted sample space is omega cross 1 to n. So that means you move particle 1, then 2, then 3, then 4, then n. We discussed that, and I already had a question about this. Second lifting is the forward metropolis algorithm. Is the lifted Markov, the lifted sample space is omega hat, is omega, the space of configurations, cross minus and plus. And take the minus into parentheses, and I say, well, let me only move in the forward direction. It's a minimum change of what you did before. Before you did move forward and backward. Now I only move forward. It's called the forward algorithm. Or I can do a particle lifted forward algorithm. Anyway, so where I do a lifting in this and a lifting in that. And this, for example, one of the algorithms is I take this disk, I move it forward. Next time I take the same disk, I move it forward. Next time I take the same disk, I move it forward. But if I have a rejection, remember, I don't allow any rejections. If I have a rejection, then I say, well, this guy is going to be the next one that's moving. So now I have some data showing you, and I have some of them we have improved ourselves, that the mixing times can be up to a million particles, can be 1 million times faster than the ones that we had before. I can talk for hours on the subject, but so what I just mean is the different organization of it's, you know, you haven't changed anything. You have omega is still the same. The moves are still the same. And you just organize the moves that you do one after the other. You organize them in a better fashion in such a way that you get out of your diffusive trap in the Chen et al. Conductance argument, and you go from diffusive to ballistic. So the good news is that these algorithms can be generalized. It's called event chain Monte Carlo algorithms. We invented that 10 years ago, or more than 10 years ago. One of the authors is David Wilson from Microsoft, a mathematician. And we came up with algorithms that actually work like this. And what they actually do, I want to show it here. I'm back to my original problem, 1 million particles, a density 20% below close packing. And this is my graph of 11.4 years. And simply reorganizing the sequence in which we did the moves got us from 11.4 years to 4.2 days. Now we are in business, because who wants to wait 10 years until you can? Well, then you have to, anyway, so then that is something that got us into business. But what I'll say is we are using the same old Metropolis algorithm. It's the same thing as before. We simply reorganize the moves and we keep memory of which was the last move we made, and we make these moves in agreement with local balance conditions. That's what. So now we have algorithms that are about a factor of 1,000 faster than the old ones, and then we can discuss things. And of course, the hundreds of people that publish pressure values for these systems at 1 million particles all got everything completely wrong, because nobody wanted to wait with the old algorithms. Nobody could afford spending so much computer time. So they simply interpreted unconverged results, which means this unconverged result was simply some kind of decoration of the initial state that they put into. In my humble opinion, they could have been a little bit more careful. So now I have 3 more slides, and I want to get into the physics of it. So this is a closed packing. This is a packing of hard disks. As you mentioned before, this is clear that this is infinite pressure, right? Because you can take out the rift, and wherever you place your rift, you destroy your configurations if you put it back together. So this is infinite pressure. So I want to discuss this infinite pressure configuration, and this infinite pressure configuration has 2 properties. First of all, it has positional long-range order. So you take the positions, put them into your Fourier program, and you get beautiful delta peaks that grow like n of the positional order, and or you throw X-rays onto this system, and you get X-ray diffraction patterns exactly at the Fourier mode. So that's called a crystal. But the hard disk system here at the packing has also, you take a Dreibein here, or Zweibein, you take your local orientation, and this also has long-range order. So you have 2 different kinds of order. One is the X-ray diffraction order, which means the positional order, and you have the orientational long-range order. Now, in 2-dimensional hard disk system, there was a famous paper written in a strange language. It's written by Rudolf Peierls. Rudolf Peierls saying that this cannot survive at finite pressure. This paper explained that there could not be crystallization in 2-dimensional finite pressure. And for Moscow, there was Lev Davidovich Landau who said the same thing, so it was considered true. And this was why people believe that in 2 dimensions there could not be any phase transitions, because these famous people have said they couldn't be. So what is also really depressing, and I don't want to depress you with it, so that was the original paper. So this is the harmonic model. We discussed that later. So they did the harmonic, so they replaced the real particle model by a harmonic model and did Fourier analysis. It's quite easy to do. And you see that you have a phonon, so the long wavelengths fluctuations kill you at finite pressure, at finite temperature. And so you don't have, and that's why people thought there could not be any phase transition. And that's what in 1953 was found. So this was the paper 1935. And the mathematically correct result, which is the Lone Star, I call that the Lone Star theorem, comes from Thomas Richthammer from University of Paderborn in Germany. And he computed the following. You take any configuration of your hard disk system at finite pressure. You take, so this is n particles here. You take a box in the middle, and you can move this box, this particle in the box, you can move this by log n to the right or to the left as you want to. And you recover a configuration of equal probability distribution. And that is 2016 is finally, if I understand correctly, the mathematically correct proof that what Piers explained was going to happen can actually be proved. So this is specific to two-dimensional hard disk. In 3 dimensions, this is not possible. In 3 dimensions, you can move this central box only by a finite amount. You cannot move it by logarithm of n. And the reason why in 3 dimensions you cannot move it makes that the diamond in three-dimensional diamond has luster. And is beautiful. Otherwise, you wouldn't see any bright diffraction. All right. So this is the Kostadis-Staudas Nobel Prize winning paper. I don't want to go into complete detail, but so they said that something could still happen. And so now so this is my last two slides. For number 1, this is the crystal. So the crystal is what I just showed before. What is the crystal? It has long-range positional order, as I just explained. The crystal has long-range orientational order. And this was proven by Phase 1940, and it can only be realized at infinite pressure as suggested by Piers, as proven by Richthammer, and as probably true for any particle system, So this crystalline state in 2 dimensions is completely excluded only except at close packing. But besides the crystal, you can have something that's called the solid. This solid has algebraic decay of positional order, which is another word of saying that the fluctuations are logarithmic from the distance between 2 particles. So this logarithm is the same as the algebraic. It has algebraic positional order, but as suggested in 1968 by Mermin in a fantastic paper, it could still have long-range orientational order. So this state is not proven to exist mathematically. But in the final slide, I'll show you that this is of course it exists. So then you have the hexatic phase. The hexatic phase is that the positional order is completely destroyed, it's short range. But the orientational order is still, it's also destroyed, but it has algebraic decay. There had been a fight for 50 years whether this phase actually existed. But of course, if you had to wait 11.4 years, you could you couldn't know anything, you couldn't even get into this, it was just impossible. And the liquid phase has short range positional order, short range orientation order, and this exists at small p as shown by Lebowitz and Penrose in 1964. So in this situation, we came up with the first actually converged, what we call converged calculations. We showed that the hexatic phase existed. Well, the solid phase was not so surprising, but we showed that the hexatic phase existed. And there was a certain, what's called a first order phase transition between the liquid and the hexatic. But of course, having an algorithm that during the life, so our simulations ran on clusters for about a year, and each of the computers that generated configurations, but about 20 or 30 or 50 configurations, so we could analyze them and had no problem. So now I come to the final thing is remarking. So you asked me to say open question to mention open questions and remark. It's not remarkable. It's just kind of fantastic, breathtaking results, mathematical results that have had incredible influence, at least on me. First incredible result is the coupling from the past algorithms by David Wilson, my collaborator. Coupling from the past is algorithms that you run them, and then they, at some point they stop and they say, well, now I have reached the equilibrium distribution. If you never heard about coupling from the past, it's just the biggest thing on the world. In the world, it has a big problem is that you cannot, so as I said, the densities that we are interested in are 0.7. Unfortunately, these algorithms break their back at density 0.3. So it's much too slow. Second, just outstanding result, Hanan, Mohani, and Montenegro. The switcheroo, it's called the switcheroo algorithm, is proven n log n mixing times. And the paper, third paper that just tops it all is the Helmut Perkins and Petty paper from Chicago. Prove that so what they were doing is the following. They found there was a Markov-Chain Monte Carlo algorithm of which they could prove that it converges in n log n. And then they said, hey, if it converges so fast, then into equilibrium, then the equilibrium state cannot be something complicated. Because to construct something complicated with single particle moves, you need a lot of time. And what I always wanted to prove, but of course, I'm just a physicist. So they actually succeeded in proving it. If you converge in n log n, then you must be a liquid. And they were lucky because they have the best bounds on how far this liquid phase actually extends. So these are just outstanding results. And then, of course, Thomas Richthammer, 2016, on his Lone Star theorem at high density. It's the only theorem that is known except of Firestone. Now I have a list of big and small open problems. The existence of crystal at finite pressure in any dimension. So there was the discussion 24. Maybe, I think, if I understand discussions with my mathematician friends, maybe there's an inroad. Maybe there's an inroad, and in a few years we'll have a first theorem in dimension 24, where somebody will prove, I know who it's going to be, where in the density 24, in dimension 24, where they can show that, well, we relax the box a little bit and we still have a crystal. That would prove the existence of a phase transition in hard sphere system. That's of course a big outstanding problem. And many years ago, Cedric Villani told me that he was going to do this. But then he got into French politics. So, but maybe now he's done with French politics. So maybe he'll do it. So if you have ideas of how to prove the existence of a crystal at finite pressure in any dimensions, and just don't lose any time because competition is out there. Or the existence of a solid at finite pressure in dimension 2. As I said, that's still not proven. Third little problem is a decent Markov-Chain Monte Carlo. I think that a million particles is not so much, and still taking 4 or 5 days until they converge. It's better than a decade, but it's nothing to be particularly proud of. And then the other thing I didn't discuss is, I said, well, these lifted Markov chains are the following: that you take your sample space, and then you take your move set, and then you mix all of this together and make a lifted sample space. Of course, then you still have to write down what is the transition matrix. And for us, it's still a bone-breaking exercise. Each time we have a new transition matrix, we have to actually prove that this transition matrix satisfies the global balance. And we actually have to go through the math. Each time I go through the math with my collaborators and students, and there must be some general principles, but we don't understand how to make this much easier. And with this, I thank you for your attention.
Are there any questions? You talk about the possible connection between small problems and the universal optimality result that everyone's trying to prove in terms of the difficulties that we face there and it's here.
I would say that your, thanks for the question. I think that your optimality result, right, is still at zero temperature, right? It is still, it's in my language, it still corresponds to, right? This optimality result is still here, right? It's still you squish you. So that's what you're trying to do. Right. What I'm saying is that once you're done with that, I mean, I completely encourage you to, I encourage you to actually do this, right? I mean, it's what is, let's say, what is, with your soft, what we call the soft sphere potential, right? The soft sphere potential, we should be able to. I mean, all of physics depends on the ground state of this thing to be a crystal, right? And I think that would be really interesting. But of course, let's say these big and small problems that I point out is now you make the box a little bit larger, right? You go from density 0.908, which is the closed packing density. You go to some density, which is 0.908 minus epsilon in a limit. And then what we know is that this crystalline state gets destroyed. It's gone. What we don't know, so what we know is it gets destroyed, which means that you have a Matchfest effect. It's called the Matchfest effect. So this thing will start to breathe, and it will breathe violently. It will breathe violently at large density, so that then you have a Fourier mode. You have the biggest Fourier mode. And this biggest Fourier mode will use up all your Boltzmann, so that it will breathe on the largest Fourier mode. What we don't know is, so that's the positional order. What we don't know is whether these things will also start to rotate. If they don't rotate, then you have what we call the solid. We are completely convinced that it's going to be like this, but of course, the evidence is not there. Right? So let's say if you can prove that I mean, you don't have to prove it because it's already proven that you have this Matchfest effect, right? This long-range phonon, we call it the long-range phonon mode that destroys positional orientation order. But it would be still interesting to understand whether the orientational order is preserved. So, but this is of course.
But so this is known in two dimensions?
No, nothing is known. Okay. The only theorem is the Richthammer theorem. But it's believed. So what it is known is in the harmonic approximation. Then you go from your real model that you want to solve into a model where you can say this is disk number one. It's connected with a spring to this guy. It's connected to a spring with this guy to a spring. And then for all times, these 6 or 7 disks are connected to each other. And then you study harmonic fluctuation. And everything that is known from piles up to later is so the theory that is used most of the time is the theory on the harmonic model. And this harmonic model has the property that in 2-dimensional you have the Matchfest effect. In 3 dimensions you don't have it. In 3 dimensions you have a real crystal, and in 2 dimensions you have also this rotation is completely suppressed. But that is taken. This is an analysis where you throw out the key element of particle system, which means that they can rearrange each other or among themselves.
Now you fix because you are fixing
the connection. That's the harmonic model.
Parameterization with a fixed configuration.
Yes, exactly. So you take a fixed configuration. I mean, that's the state of the theory. You have a fixed configuration, then you have a fixed matrix of connections, and then you study how these connections then you do harmonic analysis. You do harmonic, I mean, very simple experiments. It's much less complicated than modular forms, if I can tell you. So it's much less complicated, but of course, it gives you lots of results. And that's, for example, the only results that we have in particle systems that explain to us that crystals actually exist. Right? The crystal, as I said, a diamond, salts, and NaCl, whatever, these are crystals. You know what the crystal is? A crystal is an object that can be 1 yard by 1 yard, right? A monocrystal. And what it means is that every single particle lives like this, with fluctuations, a fraction of an angstrom with respect to its equilibrium configuration. That's a crystal. That it exists is just, it's a mystery. It's a much more mystery than all of quantum mechanics. But that it exists is only based on a harmonic model, because there's no particle system for which this state, the crystalline state, has been proven in higher dimension. And as I said, the Lone Star theorem is that in 2D, you know that this is gone. I think we have lots of discussions to have for that until Thursday. Sounds good.
I don't have a question. I just wanted to say that I'm going to tell my friend Tyler Helmut that he got his result big time, and it's going to make him very happy.
Who?
Tyler Helmut.
Oh yes, I mean that's.
I'm going to tell him that you write this.
No, I know. I mean, I'm friends with his collaborator. I mean, I told him it's just, I mean, there's nothing. I mean, no, I'm okay. Let me explain what is fantastic. So everybody is trying to prove theorems, right? For example, how far does the liquid state exist? Nobody has any idea, right? Then you do perturbation expansion, it's called the virial expansion, and you try to compute the convergence radius of the virial. I mean, it's so draft, right? I mean, you get, you want to have a virial immediately even before starting this calculation because it's so boring, right? I mean, computing. I mean, I don't know about you, but I mean, for me, computing convergence of perturbation series is just the most boring. So what they did is they said, well, hey, there is this fast algorithm. I can explain it how to. It's a switcheroo algorithm. It's beautiful. It takes 3 lines, and then there's this fast algorithm by path coupling, by path coupling, we improve the conversion in log n. And they say, hey, this cannot have any interesting physical properties. So they have a Monte Carlo algorithm for which they can prove that it's fast, and then they obtain a really fundamental physical result, which is the extension. But then they were also lucky because those people who were computing convergence, I mean, the radius of convergence of virial expansion hadn't gotten that far. And it's a complete union, right? It's Woodstock, right? It's the union of people who develop algorithms and people who develop physics. So they say, well, because this Monte Carlo algorithm has certain properties, I can say something about the physics of this. Big game, right?
So if there are any questions now, then maybe there will be during the week. I'm going to ask you about references for this.
And we have to finish our paper.
Yeah, so but some references about this 3D, 2D results.
Yes,
because it's interesting to have them there to. Okay. Yeah. Thanks. So I am going to stop the recording. Yeah. So